Wood, and this is the Physics 2212 Lab 3 magnetic field of a bar magnet. Introduction. The purpose of Lab 3 is to find the distance dependence between the magnetic field measured of a bar magnet and the magnetic field found using the Biot-Savart law. We will also find the difference between the on-axis and off-axis magnetic fields produced by the bar magnet. Finally, we will create a model in GlowScript to mathematically predict the magnetic field and compare it to the magnetic field measured in the experiment. Results. Magnetic dipole equals 3.395 amps per meter squared. The measured magnetic field equals 7.6 e to the negative 5 Tesla, and the GlowScript/simulated magnetic field equals 4.22 e to the negative 5 Tesla. Physics principles. In this lab, we will be dealing with magnetic fields using the following principles: the Biot-Savart law and the distance dependency laws. We will be using these later for calculations. Experiment. The system in this experiment was the bar magnet, and the surrounding was the room plus other existing fields. First thing we had to do once the experiment was set up was compensate for magnetic north, which is a constant field, by orienting our experiment so that the field would not affect the x component of the experiment. We then marked our phone with the approximate location of the magnometer within it for more accurate readings from the app that we installed. Experiment continued. Using the app, we then measured the data from the on-axis magnetic fields and the off-axis magnetic fields and input the data into an Excel sheet we were given. On the left, we have the on-axis data, and on the right, we have the off-axis data, including the graph. Observations. When the magnometer is moved far away from the magnet, the field experienced goes to zero. When the magnometer is moved closer to the magnet, the field from the magnet increases. From the Biot-Savart law, we know that the off-axis/perpendicular is half the value of the on-axis magnetic field value. Calculations. My y equaled to negative 2.7203x minus 14.203. The first step is to use our linearization formula to find k. We know that n is equal to the slope of the line, so n equals negative 2.7203, and that the natural log of k equals the y-intercept, which is negative 14.203. This means that k equals 6.79 e to the negative 7. We can then use the distance dependency laws to further find b bar using r equals 1. By setting b bar and b dipole to be the same, we can then find mu, the magnetic dipole created by the magnet, which is equal to 3.395 amps per meter squared. GlowScript code. The first part I did in this first image was change my mu to be 3.395. In the second image, I found the dipole using the formula. In the third, I changed the observation vectors for all those using distance and changed the B scale and the distance. And then I created the 6 different arrows using a GlowScript. On the left side, I changed it so that both the magnetic and degree or magnitude and degree of B would show up when the code was run, and I changed the dperp value to match my experimental value. This led to a B magnitude of 4.22 e to the negative 5 amps per meter squared. Results. Measured magnetic field equals 7.6 e to the negative 5 Tesla. GlowScript/simulated magnetic field equals 4.22 e to the negative 5 Tesla. This is a percentage error of 80%. The surrounding arrows perpendicular are inverse and half the value of the inline arrows on axis. Errors and assumptions. Assumptions. Assuming we are correctly orientated with Earth's magnetic field, we are assuming that 0 other magnetic fields are in the area. Errors. Magnetometer was not precisely found. Other magnetic fields are produced by electrical devices interfered with our readings, and the measurements on the ruler were not consistent. What if it was orientated incorrectly to the Earth's magnetic field? The measurements would change due to the Earth's magnetic field not affecting the y component but the x component instead. Depending on the angle that we do to the Earth's magnetic field, the x component would be greater and the y component would be lesser. What if there were 2 magnets instead of 1? The magnitude of the magnetic field would increase due to the presence of 2 magnets, but the direction of the magnetic fields produced by 1 or 2 magnets stays the same, so the direction of all the arrows would be the same. I'm Andrew Wood, and this is the Physics 2212 Lab 3 report.